Welcome to the Science for the Public lecture series. Science for the Public is an organization committed to bringing science information and issues to the general public. Visit our website for our program listings and blog. Tonight it's dark matter, and as many of you know, most of the matter in the universe is invisible and it's elusive and it's impossible to understand, and that's why you have come out here tonight to be, enlightened. It's one of the greatest mysteries in science, certainly one of the most enticing. And it's probably for that reason that it engages many of the most brilliant scientists and the most sophisticated research labs in the world. It's a very great honor to have as our guide tonight Dr. Peter Fisher, who's a veteran in this pursuit of dark matter. Dr. Fisher is a professor of physics in the physics department, at MIT, and he heads the Division of Particle and Nuclear Experimental Physics there. He also holds appointments at MIT's Laboratory for Nuclear Science and the Cobley Institute for Astrophysics and Space Research. Dr. Fisher's major research interests are dark matter and high-energy interactions. He's published extensively on neutrinos and cosmic rays. He and his team have been involved in a major experiment at CERN, and if this is designed to make high-precision measurements of cosmic rays. For all his brilliance, and despite a very hectic schedule, Dr. Fisher is very committed to and adept at translating for us non-specialists, including non-physicists, the very abstract phenomena that make up the structure of the universe. For an example that I think is wonderful, see his answers about the Large Hadron Collider on the Nova Now that he did, which you'll find on the link on our webpage for Peter Fisher. Tonight, Dr. Fisher will do three things. First, he'll tell us all the basics about dark matter, that stuff that holds the galaxies together. He'll also describe how scientists are trying to locate and identify dark matter. And finally, he'll explain the unique dark matter experiment in which he and his colleagues are engaged. Please welcome Dr. Peter Fisher.
Thank you. Well, thank you. That's a lot to live up to. I just wanted to tell you that I'm really happy to come here because I speak to the public quite frequently, the public being, MIT alumni. And, there's kind of an agenda. And at about this time, everybody's kind of sitting there knowing that they're going to be asked for something later on. So there's none of that. I'm just going to tell you about it. And it's really, I think it's great that people come out, on a night like this to learn about things like dark matter. It's actually kind of upsetting, and I'll tell you why it's upsetting in sort of a metaphysical way. I chose this title because it's the word to a song that was written by an astronomer named David Weinberg called the Dark Matter Rap. And it's actually a tremendous, it's a rap piece, and it's a tremendous piece because he goes through the entire history of dark matter in a historically correct way with footnotes. And I used to play it for, parts of it for the alumni, and finally my friend Dean Kastner told me to knock it off. Nobody liked it. It's really bad rap. But the chorus is dark matter, do we need it, where is it, how much, where is it, how much? And through the course of the song, it gets progressively more and more frantic. And I think what I want to tell you about now is kind of the franticness has reached a crescendo. And I think in the next 5 or 10 years, we're either going to find out what dark matter really is, and I'll tell you what that means to find out what dark matter really is, or we're going to find out that we're probably never going to know what it is, and we're just going to have to live with not knowing, which is not something that anybody ever really talks about, but it could happen. Okay, so I mainly show this to irritate colleagues. Science magazine is kind of the big place to publish results, particularly if they're wrong. And for their 125th anniversary, they had the 125 most important questions facing science, the 125 things we don't know. And number one is, what's the universe made of? And you know, after this, there's all kinds of, you know, gene and biology stuff. But you know, this says something about, you know, what we as a race or as a species think. You know, if you put yourself in the place of cavemen and cave women and cave children, you're sitting around the cave and you've just killed something and eaten it, and there's nobody actively trying to kill you, and you're not planning to kill them anytime soon, and everything's kind of okay. You begin to kind of take an inventory about what's around you, and there's, you know, rocks and dirt and other cave people and some bones and sinew, and you look up in the sky and there's some points in the sky, and you can't touch them, and they move around in this kind of complicated way. And it's, if anyone's been out in the desert recently and looked up at the sky, there's really just huge amount of stuff there. And we're really just drawn to it. I think, I have a good friend who's an astronomer, Paul Schechter. He just couldn't have been anything else. You know, when you look through a telescope and you see the rings around Saturn and you see the Horsehead Nebula and you see all these things, it's just astounding. And so there's been this kind of psychotic group of people drawn to look up and try to understand, you know, what's there. So the problem of dark matter is really caused by the intersection of two fields. And I'm going to give you a very short history of particle physics and a very short history of astronomy, starting with 1905 and ending up now, and to show you how they kind of really collided and created the present circumstance, which, you know, is altogether sort of unsatisfactory. So in 1905, Einstein published 5 papers, any one of which would have made a magnificent career. One of them was the special theory of relativity. And I'm going to start there in both cases and then work up to now and just tell you what's happened. A little bit later on, 1912, he published his paper on the general theory of relativity. The special theory of relativity kind of undid the separation between space and time and showed that space and time are really related in a way that was not at all obvious to people like Isaac Newton. And then in 1912, he published his general theory, which showed how gravity operates in a way that's really different than other forces. It actually acts on space-time. And so when things are deflected by a gravitational field, what they're actually doing is traveling in a straight line in a bent region of space-time. And that came out in 1912. But the special theory was added to the first ideas of quantum mechanics, the mechanics that describes very small distances inside the atom, by Dirac in 1927. And there was this really kind of amazing thing that came out of this theory. It was the idea that for every particle, there is an antiparticle. And there's actually just one equation with like 4 symbols in it. That's the Dirac equation that just says everything. You know, the really great things are simple. So for every particle, there's an antiparticle. And this very simple observation kind of launched the modern study of particle physics. So in 1936, this prediction was confirmed by Carl Anderson, who looked in cosmic rays and saw something that looked like an anti-electron. So if you remember high school chemistry, an atom has a positively charged nucleus that's kind of in the middle, and then orbiting it like a little planet is an electron. Electron's negatively charged because Ben Franklin decided electrons would be negatively charged. That's true. So there was a particle that is exactly the same as the electron, but oppositely charged. And so this guy, Anderson, saw it in cosmic rays, and that got him a Nobel Prize and an on-campus parking space at Caltech, which I think was probably more valuable. In this time, during the war and immediately afterwards, a full theory of electricity and magnetism was developed. And so this explained everything about how atoms work, how they interact, so how charged particles scatter off of each other. And this theory emerged in 1948 and is kind of the prototype for other theories of other interactions in particle physics. And I'll say a little bit more about that in a moment. So the anti-electron was 1936. 1954, the antiproton was discovered. So the simplest atom there is a hydrogen atom with a proton positively charged. It's a big heavy thing, and a little electron kind of scooting around. And so even though the proton is a very complicated object, it's got 3 quarks inside of it and all kinds of other stuff, this theory said it should have an antiparticle. And so at a custom-built accelerator at Berkeley, they actually made the first antiprotons and observed them. So these ideas really kind of built up, very, very quickly over this period of time. Owen Chamberlain and Emilio Sebgray both got Nobel Prizes and on-campus parking at Berkeley, which is probably more valuable than Caltech. So in 1976, building on a lot of work that had been done here, first quarks were discovered by Kendall, Friedman, and Taylor at MIT physicists working at Stanford. So Stanford paid for this big laboratory and this big accelerator, and Kendall and Friedman went and used it. Got Nobel Prizes and on-campus parking at MIT. And what they showed was that really inside protons and neutrons and all of this stuff, there are actually little constituents, little point-like particles called quarks. And they are real little things. They're all stuck very tightly together, and they're whizzing around. And they showed that there were 3 different kinds. And then Ting and Richter, Ting at MIT, Richter at Stanford, showed that there was actually a 4th quark. And at this point, all of this theoretical work that had been done through this time kind of collapsed together into one description of the way particles interact at the subatomic level. And so the idea is that there are 3 different kinds of interactions. There's the electromagnetic interaction, which you know about from chemistry. There's a strong interaction that holds the quarks inside of the nucleus. And there is a weak interaction that makes radioactive decay. And they all kind of follow the same rules from this original quantum theory of electricity and magnetism. There's a fancy name for it, which I'm not going to tell you because it doesn't make any sense to me. But it's not exactly carbon copies, but variations. The one thing that doesn't fit into any of this is gravity. So gravity is a completely separate thing. It bends space-time. It works over cosmological distances. But we arrive here in 1983 with a discovery at CERN made by a guy from Harvard. So people in Massachusetts are like really good at going somewhere else and using somebody else's stuff to do really good science. This discovery of the heavy light particle, which was predicted by this theory, was kind of the next to last missing piece. And the last missing piece, which is called the Higgs Boson, is the object of the efforts at CERN now. So CERN is this huge laboratory in Geneva. Actually, it's not in Geneva. It's not in any country. It's international territory, but it's between France and Switzerland, and they have a big accelerator, and they're going to bang them together and try to find the Higgs boson. But nobody really doubts that it's there, because in this period, this theory was tested, and this is where I got into the game, by people like me, at the better than 1% level. So what does that mean? It means you can use this theory to calculate that if you smash an electron into an anti-electron and you make one of these heavy photon particles and that decays in a certain way, how often does it decay? How many particles does it decay into? What kind of particles does it decay into? You can predict all of that as accurately as you want. And the actual accuracy is a fraction of 1%, largely limited by theoreticians' ability to calculate things. They're flighty people, they lose interest quickly. But, you know, I mean, who here keeps track of their checking account at the 1/10 of 1% level? So we arrive here with kind of one little unfinished piece of business called the Higgs boson, but a perfect description of everything else. So everything in this room, in the air, in us, the fundamental interactions you can calculate as accurately as you want. Now, what actually happens, how molecules and things like that form, are vast complexes of those interactions that you can't calculate easily. But that's a complexity problem. We know all of the basic rules. Okay? It's like if you know all the rules to football, and then you can study all the rules, and then you watch a play. You're not going to understand what's going on because there are 22 people all doing their thing. Okay, so we arrive here at the year 2000 with thinking that we just know everything. Okay, so over here, again, 1905, we have the theory of relativity. 1912, the mathematical description of gravity. So Einstein writes down the mathematical description of gravity. It's like 18 characters or something. It's not very complicated, but nobody can solve it for about towards the end of the Second World War. A guy named Schwarzschild, who was serving in the trenches, actually worked out a solution, in between charges. Here in the early 1920s. It was kind of the start of modern astronomy. There was an event called the Great Debate. I think it took place at the Smithsonian. And the question was, you look up in the sky, and you see lots of stars. And then you see these things that don't look like stars. They look like smudges. And the question was, what are they? Okay, so this is astronomers starting to take an inventory of things. Is that smudge a big gas cloud that's in the Milky Way, or is it like another Milky Way that's very far away? So that was actually the debate between Harlow Shapley and Curtis Heber. And it kind of became clear that there were other Milky Ways hundreds of millions of light years away, called galaxies, based on a series of measurements by Hubble, who was an astronomer. And in 1929, Hubble made an even more remarkable observation, which is he just looked at galaxies, and by measuring the reddening of light as the galaxy moves away, he could measure the velocity. And then through a kind of a complicated series of measurements, he could determine the distance to the galaxy. And he found out, number one, the most startling part is that every galaxy is moving away from the Milky Way, which means one of two things. Either the Milky Way is in a very, very special place in the universe, or that the universe is expanding in some way. He also found out that the velocity with which the galaxy was moving away was proportional to its distance. So the further away a galaxy is, the faster it's moving. So somehow space itself is just kind of inflating. And this was really very, very challenging. There were people, respectable astrophysicists well into the 1970s who just could not accept this idea that space was expanding. Worked fine in Einstein's theory, no problem. During the Second World War, there was a real explosion in the understanding of nuclear physics, and immediately after, the first idea of the origins of the universe began to take shape. So the obvious thing is you go and you measure all of these galaxies, they're all moving away, you know how far it is. You can extrapolate backwards. And so they all came from, sort of one starting point. And you can figure out that that was about 14 billion years in the past. And this was the beginning of the Big Bang theory. And Alpha, Herman, and Gamow were able to calculate how many protons, how many heliums, how many electrons would get made early in the Big Bang. So this is really kind of an amazing thing. How many protons are there in the universe? Well, they calculate it's about 10 to the 80th power. So that's 1 with 80 zeros, which sounds like a lot, but it's a finite number. The other thing that came out of this is that early in the Big Bang, as space expanded, there were these protons or these electrons, and things were moving apart. And about 400,000 years after the Big Bang, the electrons stuck onto the protons to make what's called primordial hydrogen, the original stuff of the universe. And when that happened, some light was emitted. So every time you stick an electron onto something, some light comes out. These are atomic transitions that you might have learned about in chemistry. So in these things, there are atoms with the electron getting kicked off by some radio frequency field in the tube, and then the electron sticks on, some light comes out, and we can see. This light, the Big Bang was actually a derogatory term for this theory. I forgot what the original name of the theory, but somebody said, oh, it's just a Big Bang, and it stuck. 1963, the light from the Big Bang was actually observed by Penzias and Wilson. And this was a huge thing because this light couldn't be anything else, and it's really a signal from the beginning of the universe. So during this time, there's a lot of work done on how this expansion early in the universe started, and there was the inflationary cosmology that my colleague Alan Guth developed that explained how the universe expanded very, very quickly. And a lot of measurements looking at supernova that I'll tell you in a minute. But the bottom line is about the beginning of this orange line, these guys, these astronomers, come to the particle physicists and say, well, we've measured via astronomical measurements how much stuff there is in the universe, and we've weighed it, and we've kind of taken a census, and we've found out that your stuff, the stuff that you have this great theory to describe, is 4% of the total matter in the universe, and the other 96%, we don't know what it is. So the question is this success? So we can be forgiven for this because we live on the Earth that's dominated by the stuff we know about, which is why we know about it. But in the limitless voids of the cosmos, there is all this other stuff, and we really don't have much good idea of what it is. So from the measurements, they were able to kind of categorize it into two parts. One's called dark energy, and one is called dark matter. And I will tell you very briefly what dark energy is. I don't work on it, so I don't want to emphasize it too much. But this is the statement. This is really true. In terms of fitting with our theory of fundamental interactions, there's no way to put in something like dark energy that's at all credible. There are people who try, but let me just tell you a little bit about how one kind of measurement is done. This is a galaxy, and that's a supernova, and you can see that the supernova is as bright as the black hole and billions of stars in this galaxy. So when a supernova goes off, you can really see it across the universe. So the universe is you can see it halfway across the universe. And a certain kind of supernova, called a type 1a, has a very distinct sequence of how it emits light. It gets brighter and then it dims in a certain way. And by measuring that brightening and dimming, you can calculate pretty accurately what its total energy output is. And if you know that, you can use the fact that light spreads out as 1 over radius squared to measure its distance. So you can measure how far away this is by how bright it got. Okay? It's just like, if I took a light bulb and I looked at it through a telescope and it was 10 yards away, and then I moved it to 20 yards away, it would look 1/4 as bright because it spreads out like radius squared. If I knew how bright the light bulb was, I could measure how much light hits my little telescope, divide, and figure out how far away it is. So you measure the distance that way. The other way is you can use Hubble's trick by measuring the reddening of the light, and you can use Hubble's law and measure how far away it is in a different way. So you measure one way by how fast it's moving plus Hubble's law. You measure the other way by how bright it is. And you compare. I just said all this. So this is a typical astronomer plot. Here is the measurement of how far away it is by its velocity from the reddening. It's called redshift. And then here is how bright it is. These are units of dimness, because astronomers are kind of perverse. So the larger this number, the dimmer it is. Okay? And the big thing that you can see on this plot is that when you get very far away, this is halfway across the universe. When you get a good fraction of the way across the universe, the supernovas are a little bit dimmer than they should be for their distance. And the conclusion from this is that they've been accelerated from Hubble's law. It's not just a simple linear relation, but they're getting away from us faster than they should be. And that's because there's something called dark energy that's pushing them faster than you would expect. I think actually, this is a map of the sky of the photons from the Big Bang. So this is actually a picture of what the sky looked like 400,000 years after the Big Bang, which was 13.7 billion years ago. And by analyzing these bright and dark patches, you can also make a measurement of the expansion of the universe, although it's kind of complicated to explain. But using that, the light from the Big Bang and the supernovas, it turns out that 73% of the total matter has to be this dark energy, 23% is dark matter, and 4% is ordinary stuff. And it doesn't all just come from the supernova measurement. There's been a lot of cross-checking. There are now 5 or 6 different ways of getting at this ratio, and of course you can combine them all together. So the uncertainties on these numbers are a few percent. So this picture isn't going away. This isn't some fluky thing that somebody made up in the middle of the night. Okay, so why is dark energy so weird? It's pushing the universe apart faster than it should be. And what that means, you can think of in terms of a relationship between density and pressure. So I like names for things. Boyles Law is the relationship between density in a bottle of gas and pressure in a bottle of gas. So if you take a bottle and you stuff twice as much gas into it, the pressure on the surface of the bottle doubles. And you put in twice as much again, and it doubles again. It's just called the ideal gas law. Children in the audience, a fun thing to do is take a bottle and you put some vinegar and baking soda in it and then screw the cap on really tight and leave it under some furniture or something. And the pressure will build up and it will explode because there's more gas going in that's making the pressure go up. Dark energy works in exactly the opposite way. the pressure is in, and the more dark energy you put in a bottle, if you could put it in a bottle, the more it would want to implode. So from an energy point of view, creating dark energy in space doesn't cost you anything. So the universe wants to expand so that it can have more dark energy. And there just ain't particles that can do that. So that's kind of my extent of knowledge of dark energy. There's lots more to say about it, but it's more details. What are we going to do about it? Well, the only thing we really know how to do is study more supernova, study the way galaxies are scattered around in space, and for that you need new telescopes. This is the Hubble Space Telescope, which has just been an amazing piece of equipment. I remember I was at Johns Hopkins when it launched, and it went through that horrible debacle of the optics, but it's been going just like crazy ever since. It'll die soon. And they're replacing it with this, the James Webb Space Telescope. That's probably about 5 years away. And then this is a ground-based telescope called the Large Synoptic Survey Telescope. That's really a supernova hunter. So this thing works by photographing a fair fraction of the sky every night. And then you can compare with the night before, and the differences are always interesting. Usually you can see a lot of supernovas going off. And so then you can put more points on this plot, and you can see if the plot is the same for the supernova over there and the supernova over there. You can do all kinds of things. So these are things you're going to be hearing a lot about. Okay, now dark matter, I mean, if you're just confused and unhappy with dark energy, join the club, deal with it. It's just a mess. Dark matter is a lot more tractable. And it starts with a cranky guy named Fritz Zwicky, who was really the first one he came up with the name, and he was the first one to make the key observation. This is Fritz in later years. He was an astronomer at Caltech, and he was just notoriously obnoxious. He was brilliant. But he'd come up with these ideas, like if you're an astronomer, a big thing is the atmosphere, and the atmosphere kind of jiggles around and it blurs your image. He did some calculations and found out that a shock wave from, say, a passing supersonic jet would smooth out the atmosphere for about a minute so you could make observations. So he immediately called the Navy and demanded a jet flying back and forth. He just thought like that. He did amazing things, and he's kind of unsung. There hasn't been the great fat book written by David McCullough about him. He makes this gesture because anyone who didn't agree with him was bastard. That was his term, and this was. Particularly disagreeable people were spherical bastards. So this kind of physics humor, a sphere looks the same no matter how you look at it. So if you were spherical, you just had no redeeming qualities. And the last thing I had to say about him was he was a Swiss, and my PhD advisor Felix Bohm was also a Swiss. So when I got to Caltech in '83, I asked if Zwicky was still around, and Felix is my advisor is a very formal man, but he immediately said, "Oh no, he's dead, thank God." So he's a real character, and if anyone has a yen to write a great scientific biography, I think he's ripe for it.
What's his name?
Zwicky, yeah. There's a famous yarn company in Switzerland named Zwicky Yarn. What he did was really incredible. He made a survey, one of the first surveys of a cluster of galaxies using this telescope, which you notice is not particularly big, but has a very large field of view. And this is important because when you take a survey, you want to see a lot of stars at the same time so that you can measure their brightness in a consistent way. Now, a mile or so from this is, the 100-inch Mount Wilson telescope, and everybody's fighting over who gets to use that. But you can't do surveys with really big telescope because you look at a very small patch of sky. So this was a very clever thing. This is an 18-inch Schmidt refractor, which was designed by another nutter named Schmidt. He's also quite a character. But what Zwicky looked at was this cluster of galaxies. So this is really an amazing picture. If you look at it, that's a star. That's probably a star. There's a star. All these yellow things are galaxies. All of these yellow things, every, that one right there, that little tiny one, that's probably 1 billion stars with a big black hole, probably the size of the Milky Way. And if you look, that's all you see. There are 1,000 galaxies in this cluster. Really, it's really astounding. That's a star there. Stars are pretty boring. So these are, this distance from here is probably 100 million light years. This whole mess, it's probably 50 million light years. This whole mess is about 300 million light years away. So it's one big gravitationally bound system. So they're not orbiting in circular orbits, but they're all kind of moving and swirling around each other, bound by gravitational attraction. And what Zwicky did was he really used just this picture, and he reduced it to data. So you can see there's kind of a cluster of galaxies in the middle, and then it gets fewer and fewer on the outside. He used the positions to determine the relative potential energy, and that's the energy that you have from being in a gravitational field. Like if I'm up here, I have more potential energy than I do down here because I've moved myself up, I've stored energy in the gravitational field. So the fact that these guys aren't sitting on top of each other means they've stored some energy by being apart. Kinetic energy is that, when I hit the floor, I'm moving with some velocity. Why am I moving with some velocity? Because I jumped down and accelerated in the gravitational field. So these are swirling around. He's able to, again, using the reddening of light, or this redshift, is able to measure the velocity. And what he was able to do statistically by measuring the velocity of several hundred of these and using their position was to determine the mass of the whole system. Okay? So it's really pretty simple. This was 1932 or 33. You've just decided that these are not gas clouds inside the Milky Way, but huge Milky Ways somewhere else. So what's one of the questions? Well, how much does all that stuff weigh? Right? So he was trying to weigh it. And he weighed it by relating their motion and their position using the Virial Theorem. So the most boring class you take when you're in physics is the class I teach, which is mechanics. And kind of the most boring part of mechanics is the Virial Theorem. So he paid attention during that part of the mechanics and used this theorem to determine the mass of the whole thing. And then on average, each galaxy is 1/1000th of that mass. You measure the mass of the whole thing, there are 1,000 galaxies, divide by 1,000, that's the average mass. Okay, fine, who cares? The other thing he did, again, he can figure out how much light's coming out of, say, that one by measuring how much it activated the photographic film he was using. And this was a pretty standard procedure, just how many light particles hit the film and how many, he actually counts the grains of the film that have gone dark. And you can determine how bright that collection of 1 billion stars is. Okay? You can look at a star near ours. There's a star, I think it's 3 light years away, Captain star. You know how far away it is. You can measure its brightness. You can measure its mass. And you can make a ratio of how much brightness there is to how much mass there is. And you can compare that ratio to the same ratio for that galaxy. And what he found out is that that ratio is different by a factor of 10 for that galaxy than it is for a star. So the picture that the mass of this galaxy is all in the stars is not correct. there's some other mass in that galaxy that's not related to the light output of the galaxy. And that's why it's called dark matter. It's dark. It doesn't make light. It's very simple. And that was really all there was. I mean, that is a very simple, clear argument.
So the Milky Way should also have dark matter.
Absolutely. I'll come to that. So in the rap song, after rapping about this, the line goes, and then for 40 years the dark matter problem sits because after all it's only crazy Fritz. And that's sort of true. At the time, this is 1936, it was not known, what particles there were, how galaxies operated. So nobody worried too much about the dark matter problem. In the 1970s, there was an interesting measurement made by Vera Rubin of M33, which is a galaxy not too far away. It's the Triangulum galaxy. And so here you can see the galaxy. There are the stars, and out here there aren't any stars. There's kind of some hydrogen. But again, by measuring the velocity in slices as a function of distance, which is shown here by the yellow data points, what she was able to do is measure the mass. Because if you think about the sun, the Earth's in orbit around the sun, the velocity of the Earth's orbit is related to how much mass there is inside the Earth's orbit. And so if you can measure the velocity systematically and take differences between the velocity here and the velocity here, you can figure out how much mass is in between. So the data looks like this. Now, if you just, again, took the light and assigned a certain mass to each amount of light based on what you saw from the sun, what you would expect was this. And so there's mass, a lot of mass, way out here where you can't see any stars. And so this is telling you that there's a whole lot of mass, as much mass in here, out here, actually a lot more. This is my favorite. About the same time, some guys, Ostreicher and Peoples at Princeton, got hold of a PDP-11. Does anyone remember PDP-11? Yeah. PDP-11, which is made here in Massachusetts, was the first computer that a university could afford to buy and operate. I mean, it was Digital Equipment Corporation. I think one of the saddest days of my life was when I heard they had been bought by Compaq. But the PDP-11 was the first computer where you could actually have in your office and do stuff. This is in the early 1970s. So what they did was they took a collection of mass points, like stars in a galaxy, and they started them off with the velocities that you would have if everything were rotating around the way the galaxy rotates. And then they just solved Newton's force laws and watched what happened. Just numerically, brute force solved the equations that describe the motion. And down here is time as measured by the orbit of one of the outermost things. So this is time equals 0, time equals 0.2, time equals 0.6, time equals 0.94. And what you see is that very quickly, the whole thing kind of collapses into this messy, graunchy little bar in the middle. And that's not what galaxies look like. You know what galaxies look like. I showed you a picture. They're these big, sweeping structures with certainly a concentration of matter in the middle, but spiral arms and this beautiful structure. And no matter what they did, it would collapse into this, unless they put a halo, a spherical distribution of dark matter around the whole thing. And then they would get something that looks like our galaxy. So numerically, they said, look, to get our galaxy to look the way it is, you need all this dark matter. Okay, this is actually a very recent thing, but this is extremely interesting. So all of these yellow points here are galaxies, and what's actually happening is there are two clusters of galaxies that are colliding with each other, kind of passing through each other. And overlaid on the picture of the stars are two sets of data. this pink is the intensity of X-ray emission. So when these two clusters of galaxies pass through each other, there's a lot of gas that bumps into other gas, and the gas heats up and emits X-rays. And so the pink is tracing out where most of the matter, the normal matter in the galaxies are. The blue is showing a region where the dark matter is, and that's been determined in a very complicated way called gravitational lensing based on looking at the shape, the distortion of the shape of stars and galaxies here as the light is bent by the dark matter. What you see then is this is one cluster of galaxies, and the dark matter is ahead of the normal matter going this way. This is going that way, dark matter, normal matter. And so what's happened is in the collision, the normal matter has been dragged because it's hitting the other normal matter. The dark matter, which isn't affected by the presence of normal matter or other dark matter, has run ahead. So you can actually see there's a stripping of the normal matter. This was about 3 years ago, and it's kind of now the iconic picture of dark matter. So I'm really summarizing an incredible amount of work just to give you sort of a flavor. There are about 300 galaxies that have been measured like this. This is called a rotation curve. So 300 rotation curves, they all look like this. And there have been many, many other numerical studies, observational studies. They're all saying the same thing, which is that there's about 10 times as much dark matter in a galaxy as normal matter. So kind of the dumbest picture you can make now of the situation is that this is the part of the galaxy that you're used to seeing. There's the center with the big black hole, and there are the spiral arms, and Earth's about halfway out, 45 light years. And then around the outside, roughly to scale, is this big fuzzy ball of dark matter. And this big fuzzy ball of dark matter is making the gravity in here just right so that the galaxy looks the way it does from our numerical simulations. Baryons is the fancy name for normal matter. Now, this is kind of the picture that everybody agrees is the simplest and everybody agrees is wrong. There's a huge amount of complication to this, but nobody agrees what it is. There could be clumps of denser or lesser dark matter. There are, could be little satellite galaxies. In fact, our galaxy has 2 satellite galaxies, the Large and Small Magellanic Clouds, and there are a couple other galaxies even further away. But kind of the simplest picture to think about how to look for dark matter or where it might be is this. Okay. So if you're going to look for dark matter, you've got to make a guess. And the best guess is dark matter are particles that weigh more than 100 proton masses. And that comes about because using accelerators, we've kind of found every particle with a mass less than 100 proton masses. Okay? It's like the drunk looking for his keys, under the lamp because that's where it's light. It certainly gravitationally interacts. It may or may not weakly interact with ordinary matter. That's a hope. So dark matter, to summarize to this point, all of the evidence is from astronomy and from the way dark matter gravitationally interacts. The hope is it weakly interacts with ordinary matter, because if it doesn't, it's going to be very hard to observe. Using the simple picture I showed you before, in a quart volume in this room, there are 3 dark matter particles, and they're moving with about 1,000th of the speed of light. Now, that sounds like a lot. How could you not have found dark matter if there are 3 of them in a quart? But, so a quart's maybe twice this. In 1 cubic centimeter, there are, 10 to the 25 atoms, or 1 with 25 zeros after it. So in this room, on this Earth, there's just an incredible amount of stuff that's going on that with the normal matter, so that the three particles that don't interact much, that are kind of wandering around, are very hard to find unless you do something special to find them. So let me tell you about it. So we know dark matter feels gravity. Maybe dark matter interacts with the weak force, with ordinary matter. If it does, it can bump into an ordinary atom and give it some energy. So the first thing we tried to look at, and I did this when I was a graduate student, is, here's a nucleus sitting somewhere, and a dark matter particle is going to come, and it's going to bounce off of it exactly like a pool ball. So what you need to look for is a nucleus that has a little bit of energy, about the same amount of energy as one X-ray when you get a chest X-ray, which isn't much, but something you can do. All right, so there's this dark matter, 3 per quart, moving with 1,000th the speed of light, and it's going to go like that. And my job is to find that. So the question is, how often does that happen? So if you take 2 pounds, a kilogram, current best guess is that'll happen once a year. Okay, now if you think of a kilogram of stuff, even a kilogram of stuff just sitting here very quietly, there are cosmic rays going through it, there are trace radioactive contaminants, there's probably some living cells on it because the Earth's a pretty filthy place, but there's a lot of other stuff going on. So the challenge is really signal to noise. How do you create an environment where only the dark matter does stuff? And that's what we spend our time doing. So that's a dark matter particle that's hitting a nucleus that's attached to a molecule, and the nucleus is recoiling, and as it moves along, it hits other atoms and knocks off electrons. And this is the way that particle physics is done. You count these electrons using an electronic circuit. So this was one of the very first dark matter experiments, and it was my PhD project. It's 8 diodes. Diode is about the simplest piece of electrical circuitry. But it's 8 diodes of germanium, and it's all set up so that it can collect those electrons from the nucleus after being hit by dark matter. Now, I've told you that there's a lot of stuff going on, so what we had to do is we had to make these diodes out of very pure germanium so that there weren't any radioactive contaminants. We had to surround it with copper to keep any ambient gamma rays or radioactive stuff from hitting the germanium. And then we had to surround the copper with lead. That was an economic thing. The copper is pretty expensive. The lead is cheaper, but the lead is a little bit more radioactive than the copper. So it's an optimization problem. This is about 30 centimeters of copper and 20 centimeters of lead. So there's about 12 tons of lead and about 3 tons of copper that I stacked up by hand. And I didn't get to stack it up by hand in some nice lab at Caltech. I was in this tunnel, which is a 17-mile-long tunnel through the Swiss Alps, because they're cosmic rays. Now, the cosmic rays penetrate hundreds of yards into the Earth. So a nice Alp that's about a mile high is what you need to stop those. So this is going in, and this is what the tunnel looked like. And there are actually 2 tunnels. This is the one for cars. This is the escape tunnel. And so every kilometer or so, there's a tunnel connecting the 2, and that's where we put this experiment. So I had to, this is in southern Switzerland, so I had to drive down there a couple times a week. And this is the Swiss Alps, a pretty nice place, actually. But had to go down there to work on the experiment. It's a pretty miserable place. Now, we operated this experiment for a time, and we were able to show that dark matter wasn't a heavy neutrino, which was kind of the idea. Neutrino is kind of this weird particle that doesn't interact much either, and there was this kind of idea that dark matter wasn't neutrinos, and that was pretty low-hanging fruit. So with this thing, which was actually built to do something else, we were able to retrofit it and show it wasn't neutrinos. But even with all this lead and all this copper and the Swiss Alps and blah, 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 there were still things that looked like fake signals. And there was nothing we could do to get rid of them. So it really needed a new technology. Now, doing this experiment delayed me writing my thesis for about 6 months. So when I was done with this, I was just like so disgusted with dark matter that I went and did something else for 20 years. At the same time, so we heard about this possibility of using this kind of detector to look for dark matter at a meeting in a ski resort in France. And so at that meeting was where my advisor told me, you go do this. At the same meeting, there were 3 guys, David Caldwell, Bernard Sadolet, and Blas Cabrera, who said, okay, this thing Fisher has is probably okay to start, but we want to really build something designed to detect dark matter. And their idea was actually very smart. This measured the energy of the recoiling nucleus only one way. What they decided to do was measure it 2 ways. And by measuring two ways, you could obtain much better understanding of what the particle was that got hit. So let me explain that. This is also a piece of germanium, and down here is a little electric circuit that collects electrons. Up here are a whole bunch of really, really, really sensitive thermometers. Because what they were doing is making use of the fact that when the nucleus moves along, it bangs into other nuclei and generates a little bit of heat. And only a dark matter particle can hit a nucleus to make it do that. Other things hit electrons or interact themselves, and the signal is all electronic. For the dark matter-induced events, the signal is partly heat, partly electrons. So they very intelligently decided to measure both. Tali Figueroa at MIT is working on this. So this started at the Morillon Electroweek meeting in 1988. And these guys just got their first result. So it's a tough game. Oh, by the way, because you're looking for this little tiny amount of heat, not only do you have to surround this thing with copper, not only do you have to surround it with lead, not only do you have to put it in the bottom of a mine in upper Minnesota, you also have to operate the whole thing close to absolute zero. So here you can see it. Here's a guy's glove. This is in a helium dilution refrigerator, which is one of the most god-awful complicated things ever made.
When you said they got their first result, does that mean they got something that was dark matter?
No. I'll show you. So this is just the principle that I just described. This is the total energy, and then this is the fraction of energy that's electronic. So everything that isn't dark matter shows up here. Everything that is dark matter would show up there. So this is their result. 20 years of development and 3 months of operation. So this is the same total energy fraction, and so this is just the bottom part of the plot. And these points here are interactions that they were able to explain using timing as not very interesting. The red star and blue are things that look like dark matter. And there's one. And this is the lines that they figured out from the way their things work. There's one that looks like it's dark matter. Unfortunately, they calculate and simulate everything very carefully, and they do expect statistically one that looks like that. So they can't really say that they've discovered dark matter. But what's interesting is after 20 years, this thing is a factor of 1 billion times more sensitive than my thing. It's pretty impressive. Okay, so this is just that. Dark matter isn't neutrinos, and then these guys, there's another experiment. They're now a factor of 1 billion more sensitive. So the way you get more sensitive is you build a better detector and you build a bigger detector. But some work I did with Jocelyn Monroe showed that the next generation of dark matter detectors, which will weigh about a ton, will be ultimately limited by neutrinos from the sun. which interact just like dark matter. So when I told you, we'll either get it in the next 10 years or not, this is the problem. We've come up to a place where there's an irreducible background. Like, see, these annihilations could be taking place, and protons, antiprotons, positrons, electrons, all kinds of stuff could come flying out of these different annihilations. And so you could look for those particles to see if dark matter were annihilating in our galaxy. So in 1994, a couple of people and I started thinking about how to do this. One of them is my colleague Sam Ting. So we came up with this idea that you'd look for them in space by just measuring them, by just building a detector that can tell a proton from an antiproton, a positron from an electron, and we just look at stuff from dark matter annihilation. So the way this works is this is a big magnet, and particles bend in a magnet. So if they're positively charged, they bend that way. If they're negatively charged, they bend that way. And then this blue stuff is ways of measuring their trajectory. So you measure their trajectory as they go through the magnet. You can tell how much energy they have and whether they're positive or negative. And then here, green, labeled scintillators, here and here, are timers. So when the particle goes through here, a clock starts. And when a particle comes out here, the clock stops. Now, the time to go from here to here for a cosmic ray is about 1/1000th of a second, or 3/1000ths of a second. And these clocks operate with a precision of 100 trillionths of a second. So you can measure their velocity. This is a known distance, and when you measure a time to go over a known distance, you measure the velocity. And here you measure what kind of particle it is. Now there's a rub. This is not a very big thing. This thing is about it's about 1 meter here. And this kind of thing particle physicists have been building for 40 years. This is called a magnetic spectrometer. There's some other detectors here that kind of help out, but the main thing is this curvature measurement. The problem is all of these particles from dark matter annihilation don't make it to the Earth's surface because we have this nice thick atmosphere that absorbs them. If the atmosphere didn't absorb them, we'd be dead, okay, from radiation sickness. Also asphyxiation, but we're focusing on the cosmic. So the problem is you have to get this up out of the atmosphere. And there are kind of 3 ways to do that. There was a Japanese group about 5 years before us that built a much smaller one of these, about this big. And they didn't have enough money for a balloon. They had nowhere near enough money for a satellite. So they bought a seat on a 747, on a JAL 747 that flew from Tokyo to Sydney. And it'd get up to altitude, and this thing just had its seat. It's a good thing. You can do that when you have a nationalized airline. We actually had to put it on the space shuttle, so that's it right there. And this is Discovery just after it undocked from Mir for the last time. So we had the first version of this experiment taking data on the space shuttle. I got to go and sit in mission control and listen to all the stuff going on and be a part of it. So it was really just tremendously exciting. And the only bad part is that we didn't find any dark matter. When
was that?
1998. So this is my last student's PhD thesis. This is energy of particle. This is what you expect. This is what we measured, and this is the largest amount of dark matter that could be accommodated, and it's nowhere near a signal. So we kind of didn't succeed yet again. But undaunted, we have built a much, much bigger one. And in February, it will go on the last space shuttle to the space station. And the space shuttle is going to dock here. And then this robot arm is going to grab it and put it there. And it's called the alpha magnetic spectrometer. And it's going to stay there forever. We've built it so that it will last for 20 years. there's no way to get it back, actually, because the space shuttle is the only thing that can carry it. The space shuttle is an amazing piece of hardware. It gets dumped on a lot for good reasons, but its capabilities are astounding. So if you can, go to this launch. The space shuttle launch is one of the most amazing things I've ever seen. So one last remark. The other thing you can do to look for dark matter is you can try to make them in the lab. Now, to make something with 100 proton masses, you need to bang particles together with a huge amount of energy. And as you've probably heard, this big accelerator, the Large Hadron Collider, is just starting to operate in Geneva, Switzerland. And so I can suggest several excellent people to come and talk to you about it. One lives here in Belmont. And it could be that in the next weeks or months, you read about the production of particles that could be dark matter at the Large Hadron Collider. So we're all hoping. But you know, the bottom line is, you know, we're kind of at the end of the line as far as being able to do experiments to look for both dark matter and dark energy. This Large Hadron Collider, it took 25 years to build. It's many billions of dollars. This AMS experiment, well, my colleague Sam is the guy who's in charge of numbers, and he tends to he says it costs $2 billion. I think it probably only cost about 900 million. But you know, that's real money for looking for something like dark matter. And these other experiments that look for the nucleus banging, when I casually said, oh, well, there'll be a ton, that's $200 million. So it's kind of to the point where we either find it or not. Because the next step, I don't think anybody really is too interested in paying for. But we can hope. So I'd just like to leave you with a few things. If you're interested in the Big Bang, this is the first 3 minutes by Steven Weinberg, who is a theoretical physicist and really the guy who put together particle physics as we know it now. He's a brilliant, brilliant man. And this book's probably 20 years old. It's the story of the Big Bang, but it's fabulously well written. My colleague Alan Guth explains a lot about cosmology in his book, Inflation. This is not about economics. This is a tremendous book. This book is about dark energy, and it's by Robert Kirshner, and it's very good about the science. It's very good about the sociology of astronomy. I'm also writing a book for Princeton University Press that'll be out in a year. Well, I'm finished the third draft, so maybe sooner. But it'll go into a lot more detail than this stuff. So this is the big time for dark matter. And in addition to these books, I really recommend looking at Science Magazine. They have a podcast. They have lots of online stuff. As you know, Science is a technical journal, but they have a nice section in the beginning called Editor's Choice, which is kind of a layperson's summary of what's in the technical articles. And I can only, in a given issue of Science, I can only read 2 or 3 of the articles because I don't know what the rest are about because they're all about biology. But these summaries are really pretty good. Okay, so I think that's, oh yeah, the people who paid for all of this. So this is really, it's really hard to do this because unlike a lot of other scientific enterprises, there's no big accelerator or big physics things. The thing I do are kind of one-off things. So we get a support from a lot of places at MIT, and then of course the Department of Energy and National Science Foundation. And then there's a whole other story. The dark matter detector we're building actually turns out to be good for looking for stuff you'd make atomic bombs out of. So I work with the Institute for Soldier Nanotechnology at MIT. And then this is, well, somebody can ask what WIP is. It's a whole different story. Anyway, I'll just leave you with my cat, whose name is Dark Matter. That's the one on the right is Dark Matter. That's my daughter Olympia, and I hope dark matter is going to be in our headlights pretty soon. So thanks a lot.